hjärtligt.
Good morning, everyone, and welcome to this side session that we have called Bird's Eye View on the use of artificial intelligence and satellite data for Arctic resilience. My name is Joar Kvamsås. I am the Science and Tech Officer at the British Embassy in Oslo. So this event is co-organized by the British Embassy in Oslo, together with the Alan Turing Institute and Visual Intelligence here at UIT. We will have some presentations, both from the ATI, from KSAT, and from Visual Intelligence. And then in the second half, we will have a panel discussion moderated by Robert Jensen. But before all of that, I would like to introduce the ambassador to Norway from the UK, Jan Thompson.
Thank you very much, Joar, and very nice to be here with you all. I should say, first of all, that the UK Minister for, well, she's the Minister for several things, but among those digital economy and space, Liz Lloyd, she was hoping to be here today with you at this event, very much hoping to travel. Unfortunately, personal circumstances meant she wasn't able to travel at the last moment, so she sends her apologies. So I'm actually here delivering her remarks, the remarks she would have made, so but she very much had wanted to join. So good morning, and it's a pleasure to be here in Tromsø for Arctic Frontiers at a moment when the world is really kind of looking at the High North and at the Arctic, particularly for reasons we know well. And the United Kingdom is very proud to stand alongside our Arctic partners as we confront the realities of a rapidly changing polar environment and shifting geopolitics. The effects of climate change are already felt by those who call the Arctic home and will have profound consequences globally. Rapidly changing ocean conditions also reshape the risks faced by researchers, commercial operators, and defence vessels, highlighting the need for technological innovation. Across government, academia, and industry, the UK is investing in the tools that will define the next era of Arctic resilience: AI, advanced satellite systems, and world-leading scientific infrastructure. I want to highlight how these technologies are transforming our understanding of the polar regions and helping secure the Arctic for generations to come, as well as driving key UK objectives of growth and national security. A cornerstone of this effort is Polar View, operated by the British Antarctic Survey. It has long provided trusted sea ice intelligence for vessels navigating some of the harshest waters on Earth. By integrating data from European Copernicus missions, Canadian satellites, and other platforms, Polar View supports military icebreakers, commercial shipping, research expeditions, and humanitarian operations, showing the importance of accessible, high-quality satellite data. Building on this, the UK has developed the Sea Ice Information Service, now operational aboard the RRS Sir David Attenborough. Sea Ice Information Service merges satellite feeds with real-time observations to give officers precise tactical guidance. The aim is simply to ensure any vessel in ice can access the same high-fidelity awareness as the best-equipped research ship. Work is underway to expand this capability to international partners. AI is amplifying these systems. In partnership with the Alan Turing Institute, UK researchers are creating next-generation models that forecast sea ice conditions for everything from daily navigation to 6-month planning. These tools classify ice types, predict motion, and provide insights that were impossible a decade ago, transforming routing by helping crews balance safety, speed, and fuel efficiency. AI-enabled platforms such as PolarRoute and Volt also support coordinated operations across fleets of ships, AUVs, and UAVs, enabling large-scale integrated polar data collection. Satellite AI is equally important for environmental monitoring. The Wildlife from Space team at British Antarctic Survey has combined cutting-edge imagery, machine learning, and public participation. Through projects such as Walrus from Space, more than 32,000 volunteers have helped analyze millions of images, revealing new haul-out sites, rediscovering long unseen populations, and giving Arctic communities powerful tools to protect vulnerable wildlife. The UK is also a major contributor to IceCat 3D, one of the most ambitious scientific instruments of our time. Spanning Norway, Finland, and Sweden, this new radar network will deliver unprecedented 3D imaging of the upper atmosphere, improving our understanding of space weather and strengthening our ability to track satellites and manage space debris. The UK has committed around £12 million to this transformative facility, working closely with Arctic partners as it comes online in 2026-27. Together, these initiatives reflect a clear UK vision that Arctic resilience will increasingly be built from above through satellites, AI, and strong international partnerships. No single nation can meet these challenges alone. The UK is committed to working with Norway and our Arctic partners to ensure the region remains safe, sustainable, and prosperous. AI and satellite innovation are enablers of sovereignty, security, environmental protection, and economic opportunity. Our task now is to harness them collaboratively across borders and sectors. So let's seize this moment to build a more resilient Arctic, where shared science strengthens shared security and technological leadership, delivers the world impact for the people and ecosystems of the High North. Thank you very much.
Great, thank you, Ambassador. And I will pass the word directly to our first presenter, Victoria Nockels of the Alan Turing Institute.
I think it's the other way around, actually. Sorry. That's my fault. It's Scott.
Thank you. And you've just met Victoria on stage. So Victoria and I are from the Alan Turing Institute, and I'm also at the British Antarctic Survey, and we just heard from the ambassador there on the work we're doing there. So let me move on to just present some of the work we're doing in sea ice forecasting. So 5 years ago, with the Alan Turing Institute and the British Antarctic Survey, we developed something called IceNet, which was the first pan-Arctic AI-powered sea ice forecasting system. I won't go into the details. You often in AI talks, you see some kind of diagram like this, how data is fed in on the left side, how it's jumbled around in the middle there, and then on the right-hand side, we see the outputs, the forecasts, these maps of sea ice forecasts. So the inputs are weather variables, and the model trains and condenses and extracts the information across these different convolutions in the patches and the images. We train on climate output as well, because forecasts are only good if they are forecasting into the future. We need to show the model some of that future and what that looks like. We fine tune on satellite information, and we are forecasting days ahead, weeks ahead, but also up to months ahead. And we're doing that with a fidelity and outperforming some of the traditional models, some of the leading traditional models. Let me just quickly show you this, a couple of graphs before I drop the, so this is as technical as it's going to be. But on the x-axis here, this is showing the lead time forecasting up to 90 days ahead. And on the y-axis here, so going up, we have the error, so how good the model is. And you can see that the blue line here, our AI model has a lower error forecasting out to 90 days ahead, up to 3 months ahead, relative to the traditional physics-based model. So that's for the Arctic as a whole. And then if you just zoom into the Coronation Gulf, again, you can see that the accuracy and the error is lower in our AI model out to those lead times. So I should say that the sea ice forecasting we developed was focused on concentration, so the sea ice you can see from space. And we didn't want to just stop at a nice scientific paper. We really wanted to focus on how we take that to impact. So British Antarctic Survey with the government of Nunavut, WWF, and Alan Turing Institute started then to develop a new tool to support ecological resilience in caribou migration. So these caribou migrate from the Victoria Island south when the water freezes up. And if this animation works, you'll see that here. So the caribou have these GPS collars around their neck, and they are moving south to migrate. And the blue area here, that's open water. And as the blue colors turn to greens and yellow, the ice starts to freeze up. And they'll make a run across the sea ice. And you can see that as we see more and more yellow, more and more sea ice, they run across there. So what we can use this for, the sea ice forecasts, not only to forecast the sea ice, but to forecast the migration onset. So it provides an early warning system for ecology and resilience. We just heard about the RMS Sir David Attenborough ship. So thinking about now infrastructure resilience, the key thing we care about here is not sea ice concentration or sea ice extent. And those are easy metrics to measure from satellite, but we really care about the hidden properties of sea ice, so what's below the surface, so the thickness of the sea ice and the pressure of the sea ice. And these remain important properties for shipping and operations. So pressure is hugely difficult to obtain from satellites. But we can work with proxies, and there'll be many people in the room that know far more about this than me. But the sea ice drift is absolutely key, and if we can measure the movement and changes in sea ice over time, that will give us some proxy, some information on that pressure. but we need the resolution, the granularity to be able to get down to the level that we care about, so less than a few kilometers. And we must fuse the satellite products together. So we often hear in AI models. So AI models are not just about large language models. You know, here we're using AI and machine learning to try to capture the information of the physics and predict the physics. And in order to do that at the scales that we care about, we really need to bring together lots of different types of modalities, lots of different types of sensor information. So not just satellite information, but sensors on the ground, sensors from drones, from buoys, onboard ships, etc. And AI now has caught up with that need, and that we now have the capabilities to bring all those modalities, all those types of data together. And that's only really happened in the last couple of years or so. Now, for those who do not look at sea ice maps every day, just to give you an idea of the variability and across the sea ice. So these pressure ridges here on the right-hand side are the things that we really care about. But these are white features on a white background, hugely difficult for humans, let alone AI, to monitor. But if you look at this sort of schematic here, you can really see that is what's under the ice is hugely important, and we don't want to be ploughing our ships through those scenes. At the British Antarctic Survey, we've been part of the Arctic Passion project, and part of this work is to deploy sensors on the ground to monitor the balance, the thickness, the changes in sea ice over time. And it's these surface sensors that really now need to be combined with the satellite data to really start to improve our forecasting and monitoring capabilities. And we cannot do this with the traditional approaches. Right. So last March, I was involved in a paper called Aardvark, an Aardvark model. So what was different with this model? This is an AI weather forecasting model. And to date, AI weather forecasting has started with a nice curated data set. So the data from satellite surface observations have all been combined together, and then the AI models were trained on that. The thing is, if you want to run an AI weather model or any kind of environmental model in real time, you really want to be leveraging and learning directly from those raw observations and sensors. So that's what this model did here, is it learned directly from satellite sensors, automatic weather stations, ships, and air and balloon measurements. And again, these are fed into what's called an encoder, encodes that information into a nice gridded product, and we forecast forward in time by 1 step, 2 step, and 3 steps. And this is the time AI model, the time rolling out forward in time. And then we decode that into a forecast. And these forecasts can be a nice gridded product around the world, or they could be zoomed into the location that you care about. And they can even be at the scale of a weather station, but clearly with lots of high uncertainty. So these are calibrated models to capture that uncertainty. And I will stop there, and I'll pass over now to Victoria.
Second time lucky. Oh, maybe not. No. Sounds like.
I think your presentation is going on stage now.
Third time lucky. So I'm Victoria Knuckles. I'm from the Alan Turing Institute, and this project was done in conjunction with the FCDO, working with our partners in Iceland. And we're focused around enhancing maritime and space domain awareness using AI approaches. So I head up Defence AI Research, or DARE, at the Alan Turing Institute, and we have a number of different programs: AI for Arctic Security, AI for Space and Aeronautics, Multi-Agent and Autonomous Systems, which is focused on pushing algorithms onto platforms that are limited in size, weight, and power. That could be UAV platforms, that could be satellite platforms, and it's all focused around real-time analysis. We also work on the electromagnetic environment. So we're operating in domains where we've got congested and contested electromagnetic environment, both on the radar and the communications side of things. We've worked with American partners on synthetic environments, so where you've got intermittent, noisy data sets, how can you augment that with synthetically simulated data? And finally, we're also interested in sub-threshold threats and trustworthy and interpretable and explainable AI approaches. On AI for Arctic security, we're focused on maritime domain awareness, and we have 3 primary aims. We want to be able to reduce the cognitive burden on mission planners. We want to be able to increase the probability of detecting adversary activity, and we want to shorten response times through improved asset management. We've developed a framework that's modular, that has various different components that you can work with collectively. So firstly, we're looking at optimizing sensor placement, and this is optimization considering and the adversarial context that we're increasingly operating in. We want to be able to task our assets in autonomous and efficient ways. So we're looking at multi-asset tasking. So looking at vehicle routing problems where we're considering environmental constraints. We need to be able to build this into an interface. So we've been building an operational interface that's really rapid, that enables you to view vessel movement, critical national infrastructure, but also meteorological data. As it's quite difficult to test these things physically, we're also been developing synthetic data generation, and this incorporates correlated movements with incidents and communications. You don't necessarily need to know where the vessel is right now, but where, for example, a vessel, if it needs to be rescued or there's an issue, is going to be when you reach it. So you also need to be able to do trajectory modeling. And you want to be able to do this inferring adversary positioning. Not all of our data is nicely structured and organized, so we want to be able to integrate unstructured data. So we've been looking at using large language models to do email parsing. We're dealing with lots of different kinds of data that not necessarily collected at the same time, so we want to be able to fuse that data. So we want to be able to do multi-sensor fusion. So the first part that we've looked at is this sensor optimization, or being able to position sensors. So the problem here is optimizing sensor locations. It requires knowledge of adversary goals and methodologies. Historical data can be really valuable, but it suffers from selection bias and domain shift. The sensor location can affect adversary behavior, and reinforcement learning approaches to modeling adversary tactics can be very computationally demanding. So we start with genetic algorithm approaches. We combine data-driven approaches and adversarial modeling approaches. We optimize the initial network of sensors using AIS data, so automatic identification system data, and then we do co-evolutionary approaches that enable us to identify vulnerabilities and adapt to adversarial behavior. So we optimize the location of a network of sensors. So these are heterogeneous sensors. So they may have different ranges. They may have different uncertainties associated with them. And we incorporate regional restrictions. So we're focused around the waters around Iceland. And we want to be able to optimize an entire network from scratch, or we want to be able to extend an existing network. We may also want to be able to do a cost-benefit analysis for adding additional sensors. So we've incorporated that into our approach. So when you've done that initial static sensor positioning, you then want to have an iterated approach. So red versus blue kind of approach that's robust to adversary tactics. So the problem here is sensor location could affect adversary behavior. Adversary trajectory model will have limitations and blind spots. So our solution is an iterated rounds of reinforcement learning for patrols and then for adversaries to model adaptive adversary tactics. We want to be able to combine patterns based on known adversary tactics with our reinforcement learning modeling approach. I'm going to quickly go back and forward so you can see the video whilst I talk to that. So reinforcement learning enables us to model multiple different adversary goals. That could be reaching critical infrastructure locations or crossing a region undetected, or, for example, in the case of illegal fishing, maximizing positioning at a given location. So in this little Pac-Man style video, it's trained in this case to optimize for the adversary. And in this case, our adversary is here. And this is our patrol boat, and it's set up so that the adversary has to cross through the region of the patrol boat. The black regions are regions where there are blind spots. And if I go back and forwards again, you can see that the adversary has learned to hide by passing through these walled regions undetected. So we're also looking at automated multi-asset tasking approaches. So here we want to be able to do mission planning with complex interacting constraints, where you have different task priorities and different deadlines, and you've got lots of different assets that are starting in different locations. You also have the challenge of dealing with the weather. Plans need to be efficient, but they also need to adhere to constraints and operator heuristics. So our solution is to have a mission planning as a heterogeneous vehicle routing problem, and we want to be able to encapsulate the constraints with tunable parameters, building in a knowledge of our experts. So there are a number of different use cases for this sort of asset tasking approach that we've developed. It enables quantitative comparison of mission plans. So answering questions like, how long until all tasks are done? How long until a particular task is reached? What's the impact of increasing a task's priority? We want to also combine that with synthetic data generation to inform strategic procurement decisions. So what's the average reduction in response time if an extra boat is available? Or what's the impact of assigning a fixed patrol region to one of our boats? So this is an example of a mission plan where in the top you've got 4 vehicles, and then we run it again, but for a scenario where you have 5 vehicles. And we can see in this instance for a set of 10 tasks that in the case where you've got 5 vehicles, task 1 is reached 5.5 hours earlier. So you can start to make those kinds of decisions. Often our data is unstructured, so we want to be able to take large volumes of unstructured data. So in this piece of work, we've developed an LLM that passes emails. It operates locally, so you don't require internet, and there are no GPUs. It can just run on a laptop. So here's an example of synthetically simulated unstructured text, and it's automatically structured into a structured JSON format following NATO formats. And the primary goal here is to be able to reduce the workload on operators and improve the efficiency of our workflow. Hopefully the video will run. We want to be able to do automated analysis as well. So in this case, we're taking Sentinel synthetic aperture radar imaging data, and we're doing really efficient detections in real time of vessels. And we've developed models that are 100 times smaller than state-of-the-art models that are deployable on board when you're operating in constraints where it's less than 10 watts. And this is done for field programmable gate arrays rather than GPUs, so super efficient reconfigurable capability. We're quite interested also in that integrated approach, so multimodal approaches. So this is a piece of work that we did focus not so much on maritime domain awareness, but on space domain awareness. But the methodology and approaches that we've used could equally be applied to a maritime Arctic scenario. And in this case, we've developed a foundation model that takes in data from various different sources, a combination of time series data, but also imaging data. And we've used a large volume of data from a variety of different sources, so looking at glinting of objects in orbit, that could sort of be satellites, looking at their brightness, so light curves. Also looking at hyperspectral data, so working with Strathclyde University, and orbital data. And the objective here is to do space object behavioral analytics to be able to detect anomalous behavior. There is a paper online, so I'd encourage you to go and have a look at the paper, but sort of the ultimate aim was to do anomaly detection and attitude prediction. In the maritime domain, you can do that looking at AIS and SAR imaging data. So these are sort of might not necessarily be aligned. So there can be a temporal mismatching. And our solution is to adapt a probabilistic AIS SAR matching framework to be able to combine SAR-derived locations with trajectory modeling to be able to resolve the temporal misalignment. We've also built an interface. So I think might not have time to play all of this, but in this we're doing. You can see within the interface it integrates vessel tracking, so you can play, pause, track. Infrastructure, bring in infrastructure, so it visualizes critical assets, so electrical grid. You can bring in weather information, and it's all designed to be high-performance visualization that's optimized for speed and able to run on a laptop. So to summarize, on the sort of static sensor location optimization, so we're now looking at sort of other approaches using a double Oracle framework for adversary tactics. On the multi-asset tasking, this is sort of focused around supporting operational decision-making and strategic fleet planning. We've developed our interface, that's the Maritime Operations Support Tool, and we're looking at this multi-sensor fusion integration approach. And I think in the interest of time, I will thank you.
Thank you very much, Victoria. So when working with British academics, I often try to brag about the Norwegians' ability to have very close collaboration between academia and industry and government entities. We will now have a presentation by our partners from KSAT and UIT. I believe we're starting with Sarah Björk from KSAT.
So hello everyone, my name is Sarah Björk and I will hold this co-joint presentation with Associate Professor Kristoffer Wikström, who will be on the stage after me. So our joint talk today is called Where Space, Sea and Science Meet, AI Innovation in the Arctic. I'm working as a machine learning developer at KSAT, Kongsberg Satellite Services. At KSAT, we have three main business areas. We might be most known for the ground network, where we have ground network stations at approximately 28 stations worldwide with antennas for downlinking of data from satellites that we process for our customers. We provide support for the full life cycle of a mission. We have standardized solutions for small satellites and huge constellations. In the Earth observation segment, where I'm working, our main products are the oil spill detection service and vessel detection service. But we also do satellite imagery processing. For some customers, we provide near real-time processing, and we also have some R&D products like algae bloom detection. And then we have a third segment that's called governmental programs that is completely decoupled from all other regular operational tasks due to the increased security levels that our customers have within this segment. This part also have this vessel detection service and satellite operations. And then, as we are talking about Arctic, I just wanted to give you this overview view that we compare the differences of the area of the region that a satellite can cover compared to a vessel or an airplane. So the orange region is the area that the satellite can cover within an hour. The green-blue area is the area that the airplane can cover. And a really small part of the blue-green area, you can see what the vessel can cover. So this image clearly shows the benefits of using satellites for monitoring, and especially important is this in the Arctic, due to the large region, but also the region's large distances to cities and infrastructure. And now I will go into KSAT's main products, our two AI-based products for maritime safety and environmental monitoring. Is the vessel service and the oil spill detection service, as well as abnormal reporting and detection. So if we start by looking at the vessel detection and monitoring, our platform is the Vake platform. It consists of two parts. The Overwatch, where a customer can monitor a specific area of interest, or the Pathfinder, where the customer instead can monitor a specific vessel of interest. So in the Overwatch, we help the customers to verify what the vessel's self-reported positions using the AIS tracks with using the satellite images. And if we have a correlation, we have what's called a verified AIS position. But in cases when there's no AIS tracks, but we still see the bright dots in the remote sensing images, we have what's called a dark vessel. In some cases, those implies illegal activities on the ocean. The Pathfinder, we are able to follow the full vessel activity on the shore, or ocean, I mean. We combine AIS tracks or positions, both verified and unverified, with satellite images. And we are using Clearview face recognition model to detect the same vessel among different scenes, both using SAR and optical images. And one very important thing is to, for example, detect transshipment occasions on the sea. That is when two ships are close to each other at sea, indicating that they might be loading cargo from one ship to another, which could be really interesting for a customer to understand for specific vessels they are following. Another case we might is transmitting another AIS signal than it should be. Going to the oil spill detection, we have a platform that's called the EO portal. And what you see here is a collection of all oil spill detections within a week in January now in 2026. Both man-made, because we have operators here at the mainland in the top of the island doing oil spill detection and vessel detection quality assessment. But we also have machine learning models for oil spill detections. So the purple dots and the numbers indicate the number of occurrences of oil spills around the world within this week in January. I will now show you two examples from this portal on oil spill detection. The first one is regular machine learning-based oil spill detection, where you can see the purple segmentation mask indicating the oil spill, and then you have the remote sensing image, and you can see a clear correlation between those. Or I could say that the machine learning-based oil spill detection, it was first launched this summer 2025. So before that, all operations, all oil spill detections were only man-made. But now we also deliver machine learning-based oil spill detections. Another case is using our models and aggregate data over a specific area of interest over a long time. So in this example, we have aggregated data from the west coast of Svalbard from 2010 to 2025. We run machine learning models on all products in this specific area of interest. And then we are you can see that we have a lot of oil spill overlapping in the same area. So in this case, we have used our machine learning models to detect natural oil spill seeps. The seeps could be due to like a shipwreck lying on the floor ground and leaking oil, but it could also be outbursts from the seabed of natural oil. So this is just two examples of what you can use our EO portal for oil spill detection and analytics. And we are continuously working to develop it further by incorporating oil drift models, extra input data, but also providing in the future source identification and help our operators at KSAT. And that takes me to the last slide I have today, and I will talk about our research initiatives at KSAT. We are very proud to be part of many different research initiatives, because it's important for us to follow and be on the edge of development. And that we believe we do together best, together with academia. So now we have a lot of different projects ongoing. We are partners in two ESA Arctic Field projects. One is the Oasis oil spill analytics in the Arctic using satellites and intelligent simulations that we work together with SINTEF. We will combine oil drift simulations, AI detections, and normalized historical data observations to provide a complete timeline for oil spill abnormalities in the Arctic. And then we also have the Plume project, with a collaboration between NILU and KSAT. It's a multi-mission optical data project with the aim to identify methane emissions onshore. And then we also are proud to be partners in the Visual Intelligence Center, which is a center for research-based innovation that Christopher soon will talk more about, where we, among other things, are co-supervising our PhD supervisions, and we also do a master supervision. We also have a project application we got with the Norwegian Research Council. And last week, I think our investments in research was about 10 million Norwegian crowns, but then just before the weekend, we got another large application approved. So I think our investment in research has doubled just over the weekend. And now I will leave the floor to Christopher. Thank you.
All right. Thank you, Sara. Good to be here, everyone. So my name is Christopher. I'm the PI for Earth observation in Visual Intelligence. And Visual Intelligence is Norway's leading research center for AI-based analysis of complex imagery. So it's headed by us here at UiT, together with our research partners in Norwegian Computing Center and the University of Oslo. But in this context, we have also our user partners. And here especially our collaboration with KSAT is particularly important for our Earth observation research. Now, in a field like this, you need a strong team to make progress, and fortunately we do. So together with our research partner, also KSAT, we have a large team working together to provide cutting-edge AI research for state-of-the-art Earth observation solutions. And I think Sara has shown you kind of what AI is already doing. So there's already AI solutions that are providing value to companies out there. And we've been very much part of jointly developing these things, but our job is also to look forward and see, okay, what are the problems that haven't been solved yet? So what I wanted to do was to kind of give you an idea about the problems that are next to solve. So one thing that we're working on now is letting AI models learn how to understand context. So, for instance, here you see an image of a large area, and the orange square you see there is how modern AI systems are seeing the world. So they have a very narrow view compared to what a human operator sees, who will actually look at this full image. So if you zoom in, this is actually what the AI model has seen. And you've seen this on the other presentations, that you have these small squares. And then you might say, okay, why are we not just looking at the entire image? Well, for non-technical people, it might not be clear to see, but these images are huge. So these are really big images. And these AI models are also huge. Trying to put them together, it's very practically difficult, and you haven't been able to do it really. But recent research has shown that it's possible to go beyond this kind of square and extend the context of these models. So Sigurd is a PhD who recently started, funded by the Norwegian Research Council, and his job will be tackling exactly this problem. But it's not really just confined to this image. You can also think about observations from outside the image, or observations from base station, observations from ships, measurements from all around. So this is a problem that Harald is working on, who's a PhD student in visual intelligence. And you can imagine taking in context from a wide range of different landmarks, objects, and other things that might be relevant. And here we're trying to go one step beyond kind of these small images that we look at to take in context. And I think this is within reach in the near future. But you don't have to be so imaginative to see where this is going further. So if we go back here, for instance, okay, now we can look at an image like this. If we have models that successfully understand a scene like this, we can combine scene like this. And if you remember Sara's image, where we cover essentially a huge area of this of sea, for instance, you could have models that are continuously monitoring a large area that's been impossible before. Connect that to a large language model, and you will have a model running, giving you reports continuously about activities in that area, providing a type of surveillance that would be impossible just a handful of years ago. So, developing AI that can understand contexts, one of the things that you will definitely hear more about in coming years. Now, another thing you will hear a lot about in years coming forward is going from AI as a decision support tool to a decision maker. So here I have a very simple setting to frame it. So these images you've already seen. So it's SAR images where we want to detect oil spill. And as Sara said, machine learning models are already doing quite well here. Now, they're doing quite well, not perfectly. So you can't really kind of send them out on their own. So you have some human supervision and quality control. So Dina, who did the master project with us, and KSAT, was looking into, is there any way that we can confidently say what images can we allow the model to work automatically on, and what images do we have to send to the human operators? And I think for the people not working in machine learning, you'd be surprised to hear how difficult uncertainty modeling is. So that's something we humans do really well, but that these models still have a lot to do on. And here it's a very concrete task, okay, there might be uncertainty because there's poor measurements, maybe there's lots of wind, there's other things that confuse the model. You can go in and analyze and think, okay, due to these factors, there's lots of uncertainty here. But if you think a little bit beyond what we actually want to do with these models, so let's say that we know there's an oil spill here, we know the faster we clean it up, the better it is. We're not sure based on the measurement we want now. Let's say we had an automated system sending out automated drones, taking pictures, checking, okay, now we know or we don't know, coming back, reporting, and then we send an automatic cleanup mission. That would be great, of course, but then if you want a human in the loop in this, it will take time. You will have kind of committees, people going over. What you would like is that the system could act autonomously. If you want the system to do that, you can't get around having accurate uncertainty measurements. And it will kind of open up the door also for a lot of new questions. So if we go, so usually AI systems now are some kind of decision support to humans. If we actually would like them to be decision makers, it opens up the door, for instance, for a lot of legal questions. So let's say we send an automatic drone to inspect something. Let's say that drone crashes, there's lots of weather. Who are the responsible for what happens then? What are the decisions to be made for this model to make such a decision? And here the context is Earth observation, but this is kind of a fundamental problem in AI research. How can we incorporate uncertainty into the decision making to allow AI to go from just a support system that needs to have us in the loop to actually make decisions on their own in a reliable way? So these are just two directions that we are working on moving the research front. But we'll have a discussion afterwards, and I think there's a lot of things we've been talking about in the presentations, trying to summarize some key factors. So I think we've seen in this talk that AI is already a key factor in Earth's observation. So it's being used in sea ice forecasting, vessel detection, oil spill analysis, all kinds of tools that are already in production. So there's no doubt that AI is playing an important role. Then the question is, of course, how do we move forward from this? And an interesting thing is that, when technology is not so mature, you can work in these kind of silos and synthetic settings, maybe like half real-world settings. But as the technology improves, there's less and less gains to be made in kind of these confined settings. If you actually want to make progress, you have to scale it up. And Earth observation systems with AI is getting to that area now where they're so good that, okay, to actually see how to push their limits, we need to take this to another scale. And I think, for instance, what we saw with the sea ice prediction is exactly what we see there. It's no longer just something you do on the computer of, a PhD student. You actually have to coordinate with a lot of different factors. And my point is here is that if you actually want to make progress, we who work with these things know that when you take one of these systems and you put them in the real world, all sorts of problems happen. And we can't predict them from beforehand, so we need to actually test it. And to do that, we need strong collaborations between industry, academia, industry, government, to actually test out things. And then, of course, there's a question about the computation resources required. So let's say we had one of these models that I said that continuously monitors this huge area. We're going to need compute to run that model. Where will that compute be? How will that compute look? If that's actually going to be useful in a critical scenario, can we rely on that model being cut off by some, for instance, big company? A question to be had. And then, of course, given that visual intelligence is a center for research-based innovation, I think a message that's important to get across is that the products that we see today, for instance, the oil spill analysis, vessel detection, all these kind of things, these are things that were research questions 5 years ago. We already then saw that this was a capability of AI models. It takes time to then turn them into action. But that kind of indicates that we need the research now to make progress in the future. So I think with that, I'll leave you and say thank you.
Thank you, Christopher. I think I will just invite you to take a seat, and I think I'll invite the rest of our presenters to join the panel, and I will pass the microphone directly to Robert Jensen of Visual Intelligence to moderate the discussion.
So, first of all, I would just like to thank Joar and the British Embassy in Norway. They are really supporting this event. I think it sends a very strong signal about the importance of the topic we are discussing today. So, as Joar said, my name is Robert Jensen from UiT. I would like to also to thank all of you for being here. It's a full room. Very happy to see that. So we are now in Tromsø. So Tromsø is a major hub in the space and satellite world. We're also a major hub in the AI world. So when you put that together, space plus AI, I would say that you are now in the capital of Norway when it comes to this topic. And visual intelligence, which I lead, we are very engaged in AI, of course, that's our business, but also to address the big societal changes and challenges of our time. And this is also connecting to our topic today. And also at UiT, we have some very big initiatives coming up that will also strengthen our efforts as we move on. So in the future, we'll come back to that a lot. We have our Aker N-Scale Innovation Center that we are building now as a big push. And also we're setting up something called the Arctic Institute for AI, which will be a big initiative for UiT. With that being said, let's move on now to the panel discussion. I would like to thank our panelists first for very nice introductions to the topic. So I would like to start a little bit by Arctic resilience. So that's sort of the overarching theme. And maybe people put different associations to that topic. So let's just first start a little bit. Scott, so what is it that we mean when we say Arctic resilience?
Interesting. So resilience can mean many things to many people, to many sectors, but I think it's I would argue it's being able to thrive in the face of challenge, be that environmental challenge, geopolitical challenge, economic challenge. And if we can see on the horizon the changes that are coming, then we need to make sure we're prepared for that, and that's to make sure we put in place the sensors, the satellite observation platforms that we need, the tools, but also what underlies all these tools and the satellites and the sensors is the infrastructure. And quite often it's this infrastructure, the hidden infrastructure, that can be sort of ignored. And I think we really need to make sure that we do have that holistic whole picture understanding of what is needed. And often, you heard 4 talks today, and we're all sort of tackling quite different real-world challenges, but there's a lot of synergy and overlap and similarities between these, where we are using satellites and SAR satellites, radar, and sort of imagery, visual imagery to detect change. And I guess in the face of resilience and with sort of the challenges is huge, but the budgets are also dwindling. We've got to be very creative and clever about the way we spend the money to make sure that we are working together across sectors, across industry, across government.
Thank you. So, so Victoria, so you mentioned many things in your talk, and also some challenges when it comes to Arctic resilience in the broad perspective. You mentioned observation platforms, for instance. So do you think there are some challenges when it comes, for instance, to observations in the Arctic?
There are lots of challenges in terms of having, not necessarily having widely available data sets that provide you with good ground truth. You're often operating with different resolutions of data sets. So if you're looking at an electro-optical satellite and you're trying to combine information with that from, say, a synthetic aperture radar imaging satellite, you've already got the challenge of one sees through cloud cover at nighttime, the other doesn't. You're operating in different resolutions. They're captured at different times. You're often dealing with both global spatial scales, but also localized spatial scales, and running models at different scales and integrating that together, where you've got multiple different data sets, some of which could be time series, some of which images. Being able to do that in an integrated way, where you have a good understanding of the uncertainties on your different data sets, is really challenging. We heard from KSAT around where you've got 2 vessels next to each other and you're looking at onboarding. It can be quite difficult to distinguish between whether you've got 2 vessels or 1 vessel, and that's quite crucial in terms of how you might deal with that. And you have to be able to have a level of certainty around whether is it 2, is it 1? Do you have a good understanding of your uncertainties on your data sets? So you've got challenges around cascading errors between data sets and being able to handle that. You're bringing in environmental factors as well that could impair your ability to do those kinds of assessments. We're also operating in a domain where you need to have interpretable and explainable AI approaches so that you can give a level of certainty on your decision making. And that's increasingly challenging when you're dealing with adversarial approaches. So dealing with things like poisoning of data, or also challenges, so that would be at training time, also challenges at inference time when you deploy, dealing with evasion attacks, for example. So there are lots of different challenges out there, I think.
Yeah, and maybe that connects a little bit back to resilience. So there's resilience of communities, populations, countries. changes in climate, for instance, but there's also something about the technological side, which I think you allude to quite a bit here, on the sort of the AI and machine learning side in the methods and models we develop. So we can come back to that a little bit later on also. So you all mentioned partnerships and, for instance, in the visual intelligence context, that we work so closely with industry. And Sara, you're from industry. You're from a global leader in the satellite business, KSAT. So what's your sort of view on Arctic resilience, first and foremost, KSAT's role in this? Why do you work with academia, like us at UIT? Could you say a little bit about these things?
I should maybe start to mention that as having a PhD, I started in academia and then involved into the industry. So I have both views, and I think that's really important when you meet with academia, but also government and other industry partners, to see the full view of what can be a business case for companies, but also what can be interesting, or what can research and academia help. Because like if you work in industry, you also have this operational task and you will do the day-to-day management. And that's why it's so important to split up your time, but also what you can do. And because you can't do everything in-house. And as working in the industry, you cannot follow every new research opportunities or model that's are proposed. But you still want to be on the leading edge of development. And that's why collaborations with academia is so important, because it helps us to stay on the edge. But also, instead of trying out 50 different models, we could have narrowed the gap down to 3 or 4 different, which is more convenient for us. And then we talk with the customers we have in governmental or other industrial customers that says that, okay, you have this product, but we would like it to be even better. And then together with the customers, we understand the market depth and what our customers need, and we can go back to research collaboratives such as visual intelligence or potential new collaborations, and discuss how can we meet the demands from our customers. So I think it's essential to continuously evolve what we do in the Arctic. And due to the geopolitical climate, but also if you look at the environmental climate, the Arctic is vulnerable, and we have to stay on the edge in many aspects to continue to develop and improve. I don't know if I answer all your questions, but some of them.
Yeah, I think so, and even more. Thank you for that. So, Kristoffer, you represent now academia, and we then work together with KSAT, for instance. You mentioned decisions and decision support. Maybe for the audience, machine learning is a super active field. It's all about data analysis. It's very mathematical. You could maybe say to some degree that part of the machine learning field is very much about sort of the new models, push accuracy, sometimes on sort of benchmark data sets, and maybe a little bit academic. But what about the future when it comes to being able to make decisions based on this field of AI, and especially in this context of satellites and the Arctic? Could you say something more about that, maybe?
No, I think it's going to be, I think there's a change in the field of how you think about the evaluation of these models. So now we're thinking about Arctic resilience. I think we've covered Arctic well, large area, we need satellites and measurement on the ground and combine these. And then when I think about resilience, I think about systems that are robust in the face of, let's say, noise or interference or adversary opposition. And in those situations, let's say you have a system trying to guide models or trying to make decisions. Let's say you want to ship out people going somewhere. You want that model to usually be reliable, to it makes a decision, and you can trust it even in the face of challenging situations. And I think people now are probably very familiar with language models and these kind of things, which usually do really, really well, but they also every often fail in weird ways that a human wouldn't do. And if you take these things also to, let's say we had a system that were kind of controlling a large area of the Arctic, giving suggestions to ships where they would go, I think such a system could do really well. But if it every now and then, sends a ship on off course or sends out a drone to somewhere it doesn't have to go, trust will very quickly dwindle in such a system. And I think, as you move these systems from kind of a research environment into a production environment, you'll see more and more of these cases pop up. So I think it's going to have to be a change in how we develop and train these models for them to, not do well just in the controlled setting, but that also, when we stress test them, they keep providing decisions that you can rely on. And I think, that's going to be crucial for these models to actually have an effect in the real world.
So, Scott, coming back a little bit to this, so at the Alan Turing Institute, my impression at least, a little bit from the outside, is that impact in the real world is super important. I mean, this is what's sort of driving the core of the Institute, and you've been involved in much of this, environmental monitoring. You mentioned things like sea ice forecasting, weather forecasts. So why do you think this is important also in the setting of, now we are in the Arctic and we are talking about resilience?
Yeah, interesting question. Yeah, so as you said, Robert, at the Turing Institute, but we're not alone in this. We need to demonstrate to our funders, to governments, that we're providing real impact, that we're making change, that the money, the taxpayers' money, is being well spent. And we're in this age where very, very many people around the world can take a machine learning course and play with some data and come up with some answers. So it's how do we make sure that those answers are robust. We heard about the importance of interpretability and trust. But the only way you can do that is to be working with those who are going to be using those products, using those data and pulling those products through to impact. So right at the very beginning of the design of our projects, we need to be working with those, the communities, the decision support information, people, the captains on the ship for the sea ice forecasting. We're working with the UK Met Office, and we've got colleagues in the room for the UK Met Office, where from day one we sat down together and worked out what challenge are we really trying to solve here. Just writing down a few metrics and saying we're trying to lower the error of sea ice concentration in the example I gave is not enough. And to give to sort of continue the thread with the example with the UK Met Office at the moment, we are working with the internal expert operational forecasters, and they are looking at our forecasts, but it's still a very experimental model at the moment. But what's really useful is by presenting them the forecast that our AI model is presenting, they can say, oh, this just doesn't look quite right. And, we get that two-way feedback each and every week. And I think you can't treat AI development as, something that's happened in a department sort of at the end of the building, and one day they'll create something that'll be good enough. There needs to be regular, week by week, day by day interaction. Another thing, just to add, and this is some work that we've done together, Robert, with your group in Visual Intelligence and the Turing, is interpretability and explainable AI. Now, AI models, we know, traditionally are quite expensive to be able to do just what you want them to do, to provide an output to predict, the next sentence or to predict the sea ice forecast. But if you add on top of that the ability to also to be able to explain how it got there, again, the compute budget can go up. So I think we've really got to be clear about, what do we mean by interpretability and trust? And, when do we need it? And, how making sure that humans are in the loop. We shouldn't ever get to a point where we're developing an AI model and then we just say from it's reached version 1, okay, done. We've reached version 1, we switch off the old one, we switch on the new one. We need to think about the transition between different products and tools. And there's power in diversity of tools anyway, I would say. So we should never treat AI as the new solution, but as part of one of our tools in our toolbox. And with just the last thing I'll say is that just because a model is fully interpretable and gives you the right answer each and every time. That doesn't mean that the public will trust it. So there's a journey that we need to go on to make sure that the users understand the model, that they see it's right, that we've got fallback options, that there are humans behind these decisions as well, and it's not just a computer that says yes or no.
And if I may just add a little bit there myself, I think it's also very, very important that the public sees who are actually behind the scenes. So it's people like us, and we are just ordinary people. We're not in some, kind of big tech elite or something like that. Ordinary people working at UIT or the Alan Turing Institute, KSAT. And also a point maybe that is not fully appreciated maybe is that in many situations in, let's say, geological processes, biological processes, weather is one such example, forecasting of sea ice. Today's systems are based on what we call numerical models. They are very computationally intensive, based on modeling big sets of equations about how we believe the world is governed. With machine learning AI, there's a big development now that is basically replacing, to some degree, at least in the future, many of these systems. And they can actually be less computationally expensive, even if it's GPU and compute-based. Moving on a little bit here. First of all, we'd just like to also mention that very happy that a few years ago, UIT, through Visual Intelligence and the Alan Turing Institute, we entered into this MOU, it's like a partnership that we are building, step by step, stone by stone, to advance science, but also innovation, and also sort of we do it ourselves, basically, from Norwegian and UK side. So, Victoria, what do you think about, are there some actors missing in the debate? So now we are, industry, Sara, we are some academics, but then you have also, for instance, when you talk about satellites, there are some operators somewhere, somebody owns these satellites. KSAT is a ground station operator, so they receive data and so on. But what do you think? Anything we need to inform, for instance, ESA or some operators, that's important moving on?
I think most of the actors are engaged in some capacity. So there's sort of good collaboration. So the Alan Turing Institute sits at the intersection between industry, academia, and government, and we get good engagement on all three areas. I think some of the challenges are more around things like interoperability. So if you've got different organizations operating according to different data standards, how do you broach those challenges? If you've got sort of an organization where their data is perhaps too expensive for academia, how can academia engage with that activity and inform that activity if you're having to buy very large volumes of data that's not sort of economically practical for academic organizations, or if you're operating in scenarios where there are a limited number of actors that could economically run a very, very large language model, how do you bridge that gap? How do you get access to data that perhaps only satellite operators have access to? So you've got some data sets that are sort of publicly widely available, some data sets that you can purchase, but also there are a lot of satellite operators that would collect their own data from onboard sensors, and perhaps it's crucial to be able to have some access to that in some way to be able to develop new approaches, new techniques.
Just one more question for you. So, what do you think about onboard AI on satellites? Is that something you think we will see, and why?
I mean, it depends how you determine that, because in some senses you could already argue that a lot of things are already automated. If you're operating in an environment where you're not always in communication with your satellite, you're not always in, you want to be able to automate. You've got very limited time windows in which you can downlink data. For example, you want to make that process as efficient as possible. If you lose access to an asset, being able to then be able to re-communicate is a challenge. You talked around sort of the robustness, the interpretability side of things, but you also asked a question a little bit earlier around what are some of the challenges associated with operating, particularly within an Arctic environment. So you're operating in sort of really harsh conditions. Often sensors can have hardware failures if you're operating in extreme cold scenarios. So you need to be able to adaptively alter your setup in automated ways. You might want to, for example, automate changes in terms of the way you're operating your sensor. You might want to be able to automatically adapt parameters at the sensor level with a feedback loop that enables you to automatically change exposure configurations to build in that resilience aspect. But there are lots of different components that you could consider automating somewhere closer to doing than others. So you might want to selectively send information back if you've kind of quite limited in terms of your bandwidth and your ability to downlink. Maybe you don't want to send everything back. So you might want to make decisions about when you send back data and what data you're choosing to send back at different points. Those sorts of things I think are probably more easily automatable than doing things like automated maneuvering, for example, which I think we're perhaps a long way away from being able to do.
So Sara, so when it comes to, for instance, data downlink, latency, things like this for KSAT, or just where your ground stations are, could you say something about, let's say, any challenges for a company like KSAT for this, or opportunities? Why do you have your ground stations, where you have them, and so on?
Yeah, for those of you who doesn't also familiar with satellites, many satellites are like polar orbiting, and that implies that if you have your ground stations antenna on the northern part of the Earth or in the southern part near the globe poles, you will have a longer time for the downlink of data. But we also have stations all around the world. But it makes sense to have antennas as we do at the island here in Tromsø, but also Svalbard, because it increases the time we have to downlink data. But it's still an issue that the downlink time is so short, and more customers, but also satellite owners will like the time we have to downlink all data we would like to have during the small pass they have when they pass Tromsø or Svalbard or our Troll station at Antarctica. It's quite short. So what we are developing a case that are like, it's called Hyper. It was in the news for, I don't know, within a year ago at least, that we are working to deploy satellite antennas evolving around the world, but above Earth, so that the satellite can communicate and downlink data to this Hyper constellation. And those antennas in between the satellite and the Earth can then be a collector of data, but also downlink data more frequently to Earth. And that we think will help the situation with the data access. And we are really eager to involve in this project. Another thing I think we should also discuss is that like we at KSAT doesn't really own the data, it's the satellite owners. And as someone working with machine learning, it's like, I wouldn't say that it is a problem, but you are relying on data to develop your models, independent of it's like for like research, ice models or etc. So more like I would like to raise my hand for more like commercial satellites programs that are commercially available for both academia but also like industry projects to improve our understanding of or mapping of the world. And if I could also put something on the wish list, that would also be like a combined like SAR and optical constellation. So you could take both SAR images and optical images at the same time, because it makes it easier to correlate the time differences on the and what we see on Earth. And that would be really, really interesting for like application of oil spill detection, where the ocean differs so much between, like if you look at 4 hours or 6 hour differences between a SAR image or an optical image.
That would also make life a lot easier for us machine learning people, where we spend enormous effort to try to correlate the different modalities, SAR versus optical images, to try to, fuse information from more sources, but it's not easy. So that would be a big step forward. So there's a role for policymakers. I mean, somebody needs to decide to do these kind of things, and then we need to inform, like you said now. So are there more things we need to inform policymakers? I had one thing for you, Christopher, but this is just an open question now. Okay, we'll come back to that. So one thing which is also a little bit connected to this. So Christopher, so there's a big emphasis on AI in general, of course. I mean, it is gonna really, and it is already changing society. In this context, of course. And we need people. We need people with competence in AI, and also with competence in, for instance, satellites and that type of data. So how are we going to do this?
I guess there's many ways to go about it, but I mean, primarily educating those people. And of course, we as universities have a very important role in that. But I think one thing is through kind of students up to a certain point. So we have our AI study programs and these kind of things where we teach students about how to use AI, recent technologies and these kind of things. But then, to develop experts that can move the field forward, typically that's when you become a PhD and move forward from there. And when it comes to recruitment, given how, explosive the development of AI is, it's really kind of a battle for good people. As universities, we can give interesting problems, interesting settings, but of course, big companies around the world can give good salaries for people with AI competence. So it's kind of a competition about getting these good people that can actually move forward. Let's say the issues that we would like, as opposed to improving some parts of an LLM. So I think one thing is, of course, improving our education and kind of how we do this. But I think in terms of recruitment of PhDs, it's something about giving interesting tasks, kind of showing that if you go on this path, you can work with experts from around the world and actually make a change in these things that are very relevant to many people. And that, all right, we're not going to be able to give you the salaries that you get at OpenAI, for instance, but we might actually give you a chance to learn and do something that will be relevant for a lot of people. I think maybe that's a path to recruit passionate people.
And maybe we can give people a sense of a mission. And you're a mission director, Scott.
Yes. Well, I was just going to add, and Christopher made a really good point. So we, where we're based in London, we're based in the British Library, which for those who know London, it's right around the corner from Google DeepMind. So we struggle, when we recruit, we really need to emphasize what makes us different to big tech. And don't underestimate just how passionate sort of early career researchers, how those coming out of university really want to sort of use AI for good and change the world. You know, they've got their whole life ahead of them, and they really need to think about how, you know, they can use tech to support and reduce you know, the challenges that they'll see in climate change. So that's something I think as national institutes, as universities, we really got to lean into, is to make sure that we are using tech for good, but then also not just saying it, actually doing it. So they need that, you know, if you've got a team, they need to see that day in, day out. They see that your driver is to pull it through to impact, that it's actually being incorporated into the decision-making tools, into the weather forecasts, into the environmentally aware, ecologically resilient tools. So there's one thing to say about it, and I think for years in academia we said, ultimately this is where we want to go. We'll put in a grant proposal, but, you know, the hope is that one day it gets picked up, and that's not enough anymore. We need to have collaboration and that pull through to impact. I think I have emphasized the word pull through to impact opposed to push through to impact, which I think is the way at least a lot of the academic sort of research that's happening across the community to date, you know, the last 10, 20 years or so, is very much we get a grant and then we push it through. We hope someone will take it. And that just doesn't work. It's got to be pull through to impact with the stakeholder, the decision maker there on day one. And if your team sees that and, you know, we communicate that, then I think that you know, there's a lot of good AI researchers who will apply for your job and be very excited to join your organization.
Yeah, and I think that's a bit about that mission.
Yes.
You know, you feel that something inside, and we can help with that. I think it also touches upon resilience, actually, working together. So if you work alone, there's some academia people there, there's some stakeholders there. That's not resilient, I don't think. And that's also a little bit what we do, you know, for instance, in the case at UIT Connection, to really push through to impact, in that case, with a commercial company. Kristoffer?
Yeah, I just had one more comment on kind of this with education, and also that something about the incentives for kind of academia and also, you know, public institutions, all these kind of things. You know, a normal PhD, you know, you do research, you write articles, you have to have a set amount of articles, and then you defend your PhD. And I'm not saying move away from that, you know, I'm an academic, I like that process, but in a field like AI, where it's moving so fast, and when, let's say, we have a mission we want to solve, sometimes it might not be a paper that's actually the product you want to have out. It's actually kind of a code base maybe that solves a particular task in the system. And, you know, if I come with a PhD student with this in their thesis, well, the way the system is framed now, it's not going to go very well with that PhD student. But maybe there's a way kind of how, let's say, research funders can set up these schemes that, all right, we have our traditional academic settings, but could there be kind of a different kind of output that can be evaluated for experts in PhDs that, you know, would allow us to keep up a little bit more in terms of producing products. And again, I'm not opposed to papers, that's what I do for a living, but that there could be an alternative as well.
Yeah.
Sara?
Yeah, I think maybe your last sentence in the presentation said that today's development or technology was developed like 5 years ago. So you have to have that in mind, that we need to do research. But due to the fast evolvement of AI initiatives, customer, governments, regular people are expecting solutions to come like this. And I agree with you that we have to start changing our mind of how do we collaborate to give our customers, the governmental people or like regular people, both an understanding of research does take time, but does it have to take that long time? And that, I think, is essential, that we have this tight collaboration with the industry and the researcher, that we really talk about what do we need, what should we target here, and why do we need that. So I think we could do a lot positive things together by combining our understanding of the needs, but also the struggles. yeah, that was just a signpoint.
Yeah, and Scott, for instance, you mentioned the aardvark, this
Yes.
big new thing. But it's my feeling also, read the paper, of course, and know some of the people involved. There's quite a lot of the fundamental research there
Yes.
that you were able to translate pretty quickly into impact.
Exactly. It's the translation into impact. It's being able to really clarify and define what is needed to see the change in the world. What are the current hurdles to be able to deliver the impact, to really unblock the challenges and build resilience, and then to be able to more mathematically and technologically be able to backtrack that and go, this is what we need. And often it's not about the person in the room who invented the algorithm or knows how to deploy it. It's that those groups of people that are the catalyst between bringing the right people together to the table and to initiate that discussion. And you'll be surprised just how many AI machine learning scientists get excited about working with, say, environmental data rather than another large language model sort of problem, or trying to enhance the revenue of some products. There's a uniqueness in environmental data you don't see elsewhere, and that is the modalities that we talked about today, the satellite data, the surface sensors. We know more about the surface of Mars than our ocean, so every sensor we have in the ocean really needs to be maximized to its full extent, whereas in other fields you can almost throw away half the data and you've still got enough data to give you the information you need. So it's really working with the real world challenges, the lack of data, sometimes what feels like too much data, but just because we've got too much data doesn't mean we've got too much information. And it's just really trying to bring all those together. And that creates a really exciting machine learning AI challenge, which it's hard to see in some other fields.
So a bird's eye view, I would say, in the sense of, for instance, working with the environmental challenges. Machine learning AI is there, it's fundamentally important, and actually also contributing to, I would say, national security, to help, let's say, turn the tide maybe in uncertain times, to connect back to the topic. And I think partnerships, that's really the key to resilience between UK, Norway, for instance, academia, industry, and governments. And the ambassador just left the room. I just want to thank her, so you all do that on behalf of all of us, for opening this session. Thank you, Joar, and maybe you want to say a couple of final remarks. Thanks to all of you, thanks to the audience. Joar?
Yes, and yeah, absolutely. Thanks to all of you. I will say, we're talking a lot about collaborations, problem sets, and the importance of having researchers like yourself close to the practical problems. So I know at least Scott and Victoria will be here for the duration of the program, and this is my invitation. If you see them, go up to them and tell them about your problems. I'm just going to drop that on you. Yes, all of them. They're very generalists. And I just want to thank, yes, of course, Robert and Visual Intelligence, UIT, and Alan Turing Institute. And thank you very much, and enjoy the rest of the conference.
Thank you.